SwayamPrabha. Digital India. Educated India.
I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. The topic of this lecture is Global State and Snapshot Recording Algorithms. So, content of this lecture. In this lecture, we will discuss about the global states, that is the consistent states and inconsistent states, the model of communication and snapshot algorithm. Specifically, we will talk about a specific algorithm for recording the global state in the distributed system, that is the Chandy-Lampert algorithm to record the global snapshot in any running distributed system. And edge computing, edge cloud system is a perfect example of the distributed system. Let us see what is a snapshot. So, you collect the people at one place and take a snapshot, take a picture. Here you can see that different head of the countries are standing, and here our prime minister is also standing. So, all head of the countries are gathered at one place, that is to collect at one place and take a snapshot. This is the traditional way. However, if they are distributed at different places and will not come at one place to collect at one place, yet you want to take a snapshot. So, this is called a distributed snapshot. So, how do you calculate such distributed snapshot, and that is very common in the distributed system. The example of a distributed system, you can also say edge and a cloud system is a distributed system. So, what do you mean by taking the global snapshot for debugging purpose, for various other applications? This snapshot sometimes very much useful. So, let us see about the algorithm, how we are going to take the global snapshot, where it is not possible to collect at one place and take the snapshot. Now, let us see in the cloud the global snapshot. What do you mean by the global snapshot in a cloud system? So, in a cloud, each application or the service is running on multiple servers. So, that means one application requires several servers to run, or maybe several machines are running different servers, different applications. Now, servers handling these concurrent events and interacting with each other, and the ability to obtain a global snapshot of a system is often sometimes important even in the cloud or in an edge system. Now, some of the uses of having this kind of global snapshot in the system is the checkpointing. That means, you can restart the distributed application on failure. So, what is that closest point where not much loss is there? So, that is called checkpointing, and checkpointing is also based on the global snapshot. The second is, your application is in the garbage collection of the objects. So, the objects is the server that do not have any other objects that is pointed to them becomes often orphan, and garbage collection deals with such an object, and that is also required to take the global snapshot for garbage collection of the objects. Then another important application is called deadlock detection, and it is useful in the database transaction system. So, that deadlock detection also requires the global snapshot and then find out this particular this deadlock in a distributed system. So, in a transaction system, that is the deadlock detection is being performed with the help of global snapshot. Termination of a computation in a distributed system, such as edge system or a cloud system, when the computation will finish, it is useful in such computing system sometimes for understanding whether the application is terminated or is still undergoing. So, this also requires a global snapshot. So, let us understand this algorithm, how the global snapshot. Before that, we have to understand some of the basics or preliminaries about the global state. So, recording a global state in a distributed system on the fly, that means without stopping, how are we going to take the global snapshot on the fly is an important paradigm. That means, systems we cannot stop, yet we want to take the record the global state. That is, recording the global state on the fly is important paradigm. Now, this particular system, that is called a distributed system, has following characteristics. First thing is that it lacks the global shared memory. There is no global clock, and also the messages are having unpredictable amount of delays in the distributed system. Under this particular model, taking the global snapshot problem becomes non-trivial. So, first we will define the consistent global states and discuss the issues to be addressed to compute the consistent distributed snapshots, and then we will discuss about the algorithm to determine on the fly such snapshots. Let us consider the system model. The system consists of the collection of n processes that are connected by the channel, and we assume that there are no globally shared memory and the physical clock, and the processes communicate by passing the messages through the communication channel. Let C I j be a channel from process I to process j, we call it as channel C I j, and the state is denoted by state of a channel S C I j. So, the actions performed by a process are modeled as three type of events: the internal events, the message send event, and the message receive event. So, as we know that the actions which are performed by a process, actions performed by the process are three types. One is called internal events, message send event, and message receive event. Now, for a message Mij, that is sent by a process I to j, send of Mij and receive of Mij denotes its send and receive event. Now, at any instant, the state of a process Pij is denoted by local state of process I is a result of the sequence of all the events executed by Pi till that time. Now, for an event E and a process state LSI, if E is an element or E is a member of that set called LSI, that is local state, that is state of a process at any instant of time. That means, E belongs to the sequence of events that have taken place, that have taken process Pi to the state LSI. For an event E and a process state LSI, E is not belong to LSI, that means, E does not belong to the sequence of events that have been taken process Pi to LSI. Now, for a channel, Cij, the following set of messages can be defined on the local state of the process I and j. So, transit means that LSI comma LSJ, transit means the message it contains a message Mij, where send of Mij is in LSI and receive of Mij is not in LSJ, that means, it is in transit. Now, let us see about the consistent global state. So, a global state in a distributed system is a collection of local states of the process and the channels. So, notably the global state is defined as the summation or the union of all the local states of a process I and the state of a channel I j, that is the union of all I and j, that becomes the state of a channel. So, global state G s is a consistent global state if it satisfies two conditions, that is C 1 and C 2. Condition C 1 says that send of M I j is recorded in the local state of I such that the message M I j is in state of a channel of I j or mutually exclusive or receive of M I j is in L S j, that is an exclusive OR, that is called send of M I j is in L S I. Send of M I j is not in L S I, this implies that M I j, that is the message, is not in state of a channel and also receive of message is also not in the local state of a channel. So, this is called a global state if it satisfies these two conditions, that is send is already there, that is the message is being sent from I to j, it is in local state j. So, that means either it is in channel or it is being received by the j. The send, if it is not in send of M I j, that particular local state, that means neither the message is in channel nor it is being received. So, this is called consistent global state. So, let us take this particular example over here. So, in a distributed system, here the space time diagram of a distributed execution is shown. So, here the global state G S 1 consists of local state L S 1 of 1, L S 2 of 3, L S 2 of 3, L S 1 of 1, then L S 3 of 2, then L S 3 of 3, then L S 2 of 4. So, let us see about this particular state. So, this state is inconsistent. Why? Because you can see that it will cover a message which is received. This particular message E22, that is in this particular global state G S 1 is inconsistent. Why? Because this particular message, that is the event E22 exist, that is E22 exist in G S 1 such that this does not satisfy C 1 and C 2 criteria. This implies that C 1 and C 2 are violated. Why? Let us see, is inconsistent because the state of P 2 here has recorded the receipt of a message M I j, sorry, receipt of the message 1 2, this is M 1 2. However, the state of P 1 has not recorded its send, like E 1 2 has not recorded, but the receive of message is recorded. So, therefore, this becomes violation. Whereas, on contrary, the global state G S 2 consists of local state L S 1, where G S 2 consists of L S 1 2, then L S 2 4, then LS 34 and then LS 24. So, here you can see that the send is recorded, but the receive is not recorded. So, it satisfies both C 1 and C 2. So, it is a consistent global state. And that is what shown over here. Now, let us see about GS3. GS3 state says that LS1 by 2. So, LS1 by 2 and then LS2 3 and then LS3 4 and then LS2 4. Now, here you can see that this particular global state does not see any message which is flowing or which is sent, but not received. So, that means all the channels are empty and all the message which are sent has been received. So, in this case this particular state is not only consistent, but it is called a strongly consistent global state. So, GS3 is not only consistent global state, but it is called a strongly consistent global state. So, therefore, let us define about the global state is the union of all the local state and the union of all the state of a channel is transitless. If and only if the state of all the channels is empty, that means then in that case thus the channels are recorded as empty in the transitless global state. So, a global state is strongly consistent if it is transitless as well as it is consistent, that we have seen that global state 3 in the previous figure, that this is the strongly consistent global state. So, recording the global state of a distributed system is important paradigm when one is interested in analyzing, monitoring and testing or verifying the properties of a distributed system and the algorithms. So, design of efficient methods for recording the global state of a distributed system is important. Now, let us see through this example that here this is the strongly consistent GS3, which is S12, LS12, then LS23, then LS34 and LS24. So, you can see that it is transitless global state 3 is transitless and it is a consistent global state. Therefore, it is a strongly consistent global state. Now, let us see about the issues in recording a global state. So, there are following two issues which are need to be addressed. One is that how to distinguish between the messages to be recorded in the snapshot from those not to be recorded in the snapshot. Now, any message that is sent by a process before recording its snapshot must be recorded in the global state. Must be recorded in the global state, that is from the condition number 1. So, any state that is sent by a process after recording its snapshot must not be recorded in the global snapshot. So, how to determine the instance when the process takes its snapshot? So, a process P j must record its snapshot before processing a message mij that was sent by a process I after recording its snapshot. So, let us see the example of a money transfer. Let us see that let S1 and S2 be the two distinct sides of distributed system which maintains the bank account. Bank account A and B respectively. Now, site A site refers to a process in this example let the communication channel from site S1 to site S2 and from site S2 to S1 is denoted by C12 and C21 respectively. Consider the following sequence of action which are also illustrated in the timing diagram. At time t0, initially the account A has $600 and account B has $200 and channel of state from 1 to 2 is 0 and channel from 2 to 1 is equal to 0. Now, at time t1, this is at time t0, at time t1 site S1 initiates a transfer of $50 from account A to B. Then in that case site S1 initiates, so the account A is decremented by $50. So, A will become 550 and request for $50 credit. So, account B is sent on state of the channel 1 2 to the site S2 and the account becomes. So, here the state of the channel makes the $50 and the account become 0 this one and here it is not changed anything and C12 becomes so C21 become. So, rest of the things are same. Now, at time t2 the site S2 initiates a transfer of $80 from account B to A. Now, let us see about site S2 where B is there and B is having 200, then in that case site S2 initiates a transfer of $800 from account B to A. So, $80 is to be subtracted and the channel 2 to 1 will be then 80, in that case it will become 120. So, account of B will become 120 and the request for 80 will be credited to the channel that is 2 to 1 account, then in that case A will become 550 channel and the channel 1 2 will become 50. Here the channel 2 1 will become 80 and the account of B will become 120. Now, at time t3, if you consider the site S1 receives a message of 80 credit, that means this C2 is received here in time t3 for $80 credit to the account A and update the account A. So, account A will have 550 plus 80, that is 630 and account B will still be 120 and C12 will be again $50 and C21 will become 0. Why? Because the channel is now empty. Now, at time t4 the site S2 receives the message here, receives the message for 50 credit to account B and updates the account B. So, B will become 120 plus 50, that is 170 and both the channel 2 1 is equal to 0 1 2 will become 0 in that case, and A will become 630. And this we can see from here, these kind of interaction. Now, suppose the local state of account A is recorded at time 2 at time t 0 to show that A is 600 and the local state of B and the local state of account B and the channel are recorded at time t 2 to show that they are 120, 50 and 80. Then the recorded global state shows 850 in the system, that is 50 extra, and this becomes inconsistent. So, the reason for inconsistency is that account A state was recorded before $50 was transferred to account B using the channel C12 was initiated, whereas the channel C12's state was recorded after the $50 transfer was initiated. This example shows that the recording a global state of a distributed system is not a trivial task. Recording activities of the individual component must coordinate appropriately then in that case. So, meaning to say that if let us say the global state recording is happening in this particular manner, then this may be inconsistent state. Why? Because here if let us say this is being recorded in this particular state, then this will be an inconsistent, because here the send of a message is not captured while the receipt of a message is being captured. So, such a recording is called inconsistent. That is what is shown over here. Now, let us see about the model of communication. Recall that there are three models of communication. One is called FIFO, the other is called non-FIFO, third one is called causal ordering. FIFO, each channel acts as first in first out message queues, and thus the message ordering is preserved by the channel. Non-FIFO model, that is the channel acts like a set in which the sender process adds the message and the receiver process removes the message in any random order, and causal ordering of a message satisfies the following property, that for any two messages Mij and Mkj, where j is common over here, that is if send of Mij is happened before send of Mkj, then the receive of Mij also should be before the receive of Mkj. This is called causal ordering, causal delivery of the messages. Now, let us see about the Chandy-Lampert's algorithm for FIFO channels. So, Chandy-Lampert algorithm uses the control messages called the markers, whose role in the FIFO system is to separate the messages in the channel. So, after the site has recorded a snapshot, it sends a marker message along all of the outgoing channel before sending out any more messages. A marker separates the message in the channel into those to be included in the snapshot from those not to be recorded in the snapshot. So, process must record a snapshot no later than when it receives a message, when it receives a marker or any of its incoming channels. The algorithm can be initiated by any process by executing the marker sending rule, by which it records its local state and sends the marker on each outgoing channel. The process executes a marker receiving rule on receiving a marker. If a process has not received its local state, it records the state of the channel on which the marker is received as empty and executes the marker sending rule or record its local state. So, again I am repeating, a process executes the marker receiving rule on receiving a marker. If a process has not yet recorded its local state, it records the state of a channel on which the marker is received as empty and executes the marker sending rule to record its local state. The algorithm terminates after each process has received a marker on all of its incoming channels. All the local snapshot gets disseminated to all other processes, and all processes can determine the global state. So, let us see the algorithm. So, marker sending rule for process I records its state. For each outgoing channel C on which a marker has not been sent, I sends a marker along C before I sends further messages along C. Marker receiving rule for a process J. So, on receiving a marker along channel C, if J has not recorded its state, then record the state of channel C as empty and follow the marker sending rule. Else record the state of C as the set of messages received along C after J's state was recorded and before J received the marker along C. Now, let us see the properties of the recorded global state. The recorded global state may not correspond to any of the global states that occur during the computation. Now, consider two possible executions of the snapshot algorithm for the previous money transfer. Now, before that, let me again review the Chandy-Lampert's algorithm before we run through the algorithm. So, marker sending rule for a process I says that for a process I records its state. Now, for each outgoing channel, let us say that this is the graph, and you will understand here. Now, marker sending rule for a process I, let us say this is process I records its state. And for each outgoing channel C on which the marker has not sent, I sends the marker along the channel C before it sends further messages along C. So, it sends a marker in this channel. Now, marker receiving rule for a process J, let us say this is process J along the channel C. So, if J has not recorded its state, then record the state of C as empty and follow the marker sending rule, that is rule 1. So, what rule 1 says that the process then record its state and for each outgoing channel, that is this one, on which the marker has not been sent, I sends a marker along C before it sends further messages. So, it sends a marker here in this particular channel. Now, this particular, let us say K, again else, for example, J record on J, what happens is, let us say that So, for example, when I will receive the marker which is sent by j. So, let us see what will happen, that on receiving the marker along the channel C, if j has not recorded, since j has recorded. So, it will follow the else part. So, record the state of C as the set of messages received along C after j's state was recorded. So, here you can see that record the state of channel C as the set of messages received along C after j's state was recorded. After j's state was recorded, it has not received any message, and before j received this particular marker message. So, it will not do anything for this particular message, whereas this particular message, when it is received, it will then run the marker receiving rule. So, on receiving the marker along the channel, if the k has not recorded, then it will record the state of a channel, as empty, and follow the marker sending rule. So, it will, in the marker sending rule, it will record the state, and then for each outgoing channel it will send the marker. So, you can see that eventually all the states will record their states in this global state recording algorithm. Now, let us consider two possible executions of snapshot algorithm for previous money transfer example. Now, here let us see this particular example of the markers. So, here it records the state of a channel at this instance. So, if it records the state of a channel, so that means it records the state at this point. So, what is the state at this point is, let us say that it is A is here, yeah, A is 550, at this point of time, and then the state of a channel here is 50, and the other side it is 80. Now, this particular marker, when it is received at the site S2, then what it does is it will check whether the B has recorded its state or not. Before that it has not recorded. So, it will record its state and then send. Let us see about all that details. So, the marker showing red dashed. So, site S1 will initiate just after the time t1, the site S1 records state A55550 that we have told, and they send the marker to the site S2. The marker is received by site S2 after time t4. When site S2 receive the marker, it records state as 170. So, it records its state as 170, that we have already told, and the state of a channel as 0, and sends the marker along C21. When site S1 receives this marker, it records the state of the channel C21 as 80. When it receives it, it receives the site channel as 80. It records it state of the channel C21 as 80, because this channel C21 has sent the 80. So, it will, the channel state was 80 here in this case. So, 80 will be recorded, and this is the system which is of the recorded global state. So, here you can see again So, this particular message is sent over here. So, it will record the global state A is equal to 550, and then you know that it will record the global state of channel B as, because it is received the message, it has not recorded any state. So, it will record the state of C21 as 0 and B as 170, and channel C21 it has recorded as 80. So, 800 amount in the system is conserved, you can see. Now, let us see about the other example, the marker shown in the green dotted. So, you can see that here after recording this A is equal to 600, it sends the marker sending rule, and when it receives to this particular Y, when receives the marker, and it will then record its state 1 to 0 and then record its global state of B as 120 and then send the marker sending rule here in this case. When the marker is received at this end, it will record the state, because it has already recorded. So, it will record the state of the channel since it has received 80. Therefore, here also these kind of. So, let us see about the properties of the recorded global state. So, in both the cases, in both these possible runs of the algorithm, the recorded global state never occurred in the execution. This happens because the process can change its state asynchronously before the marker is sent or received by the other states, and the other sites record their states. But the system could have passed through the recorded state in some equivalent execution. So, the recorded global state is a valid state in an equivalent execution, and if the stable property, that is the property that persists, holds in the system before the snapshot begins, it holds in the recorded global snapshot. Therefore, the recorded global state is useful in detecting these kind of scenarios. Now, let us see the conclusion. So, recorded global state of the distributed system is an important paradigm in the design of distributed system and the design of efficient methods of recording the global state is an important issue. So, in the lecture first discussed the formal definition of the global state of a distributed system and issues related to its capture, and then we have discussed the Chandy-Lampert algorithm to record the global state of a distributed system. So, what we have seen in this particular approach is the Chandy-Lampert's algorithm, which is very good at sending the marker sending rules and recording the global state without stopping the without stopping the distributed system, that is in the edge and the cloud. It gives often a very good way of taking the global snapshot recording algorithm. Thank you.